Alrighty, well, as we're getting set up, there are some materials here. Like I say, I'll give it another minute or so for people to join. There are definitely some different materials here that go along with this workshop. One is there's a slide deck. It's a rather large slide deck. There's a lot of links out to other tutorials and articles, primary sources, etc. So I try to include, I try to err on the side of including far too many links in my slide decks. And frankly, there's a book in progress. So this deck is sort of a rough draft on a few of the chapters. But hopefully there's some good background material if there's any sections you want to do more of a deep dive into. There's definitely a lot more material in overall for what we have in the open source repo, what we have in the book in development. There's probably about a 6-hour course there. We only have 2.5 hours today, so this will be an introduction to it. But if you want to do a deep dive in any particular part, hopefully there's more background material. And the other thing that's, of course, listed on the workshop description is, let me take this up. Sorry, nope, not that one. Here we go. I'll put this in a chat, but you probably should have seen from the resources listed on the workshop. There's an open source repository on GitHub. It's under Darwin AI. It's called KG Lab. And I'll just make sure to put this into chat here. So there's a code repository, and I will be running through the code when we show hands-on examples. But if you want to load this up on your laptop, or if you want to run it in the cloud, this is a Python library. It's actively being used in a few different commercial settings, but also being used for instruction in some places. We have a number of developers contributing on it, and it's a lot of the basis for what we'll be covering today. If you do use Docker, there is a Docker Compose for this here, although if you use pip or conda, there's instructions about installing it as well. If you have any problems with installing it because of, well, frankly, on Apple and Microsoft, on Mac and Windows respectively, this is being tested, but there are definitely situations where both Apple and Microsoft make it very difficult to install code, particularly when you get into some of the machine learning libraries. So if you do have any troubles with install, I'm eager to hear and try and troubleshoot, but I'll be showing all the code as well. And frankly, Apple in particular is making machine learning libraries more and more difficult for people to use. Ergo, everybody moves off to the cloud or they get Linux laptops. But for what it's worth, I'm actually running from a MacBook Pro. Let's see, other materials. Let me go back to, let's see, getting started, KG Lab. There's also some documentation here. I'll post this. Docs. So the tutorial itself, we have some online documentation for the code. There's a website that I've just posted, and under Darwin AI/docs/KGL, there's a section called tutorial, and it has a syllabus for what we'll be covering today, but it has a lot more material, reference material, etc., as well as, you know, glossary, bibliography, all the rest. Okay, and let me jump back and see just how many people have joined. If I can get back to participants. Good, okay, we've got 41 people in right now. I think we can call it a quorum. Let's get started. And I'll turn off the chat there. Okay, so hi, welcome to our tutorial about graph-based data science. My name is Paco Nathan, and I'll be leading through the discussion. For what it's worth, I'm lead committer on an open source project that we'll be using today. It in itself is mostly an integration of several other open source projects. So what our team has been doing has been to build out integration paths. And I should talk a little bit about the motivations for this course. Uh, Number one, it is about open source libraries in Python for leveraging different forms of graph technologies. We're not going to be doing a deep dive in every area of graph technology. That is far beyond the scope of what we could cover in 2 hours, but we will give some introduction to the popular areas. And the rationale for this is that there are a number of different camps when you work in terms of graph technologies. There are certainly the people who have been doing graph algorithms, and those are very valuable at scale. There's also a lot of work in terms of different types of graph queries and different types of graph databases. There's also work in interactive visualizations of linked data. There's work in deep learning with embedding. There's also work in probabilistic graphs, where you're looking at, say, Bayesian networks or causality or other forms of statistical relational learning. A problem it has been traditionally that these camps really don't talk with each other. And so if you're using popular open source libraries for graph algorithms, such as iGraph or NetworkX, those do not work very well with the systems that provide graph queries. And so for people who work in this space, some of us who've been working in this area have just over and over had to write a lot of glue code to try to integrate, because we're working in one framework when we run a query, and then in an entirely different framework, totally different library for representing graph when you work in the algorithm side. And then when you want to visualize, you shift over into yet another framework. And then if you want to throw deep learning into the mix or some probabilistic methods, you're off on other frameworks. So what we have been trying to do since last October was to build up an abstraction layer in Python that can speak with these different camps and provide, if you will, a Pythonic approach, idiomatic approach to integrating them, testing their integrations, providing tutorials to show how they can be leveraged together. But more than that, making it something that fits into, say, pandas and scikit-learn and the usual suspects when you're working with data science. And so ergo the name, graph data science, we're showing how to use graph technologies in a data science context. And the prerequisites for this, really, if you have some experience in Python, if you can read and write a 20-line program in Python, you should be good to go. We're not going to throw too many curveballs in terms of the programming required. Now, what we're doing in these libraries, there are some areas of relatively sophisticated software engineering, particularly at scale, particularly using distributed systems and hardware acceleration, things like that. So if you want to drill down or talk about those issues, we can definitely go long on the software engineering side, but it's not a prerequisite to come in and use this. And the other prereq is just, are you interested in working with graphs? And we'll cover a little bit about graph thinking as sort of a introduction here. If you have some math background, certainly algebra, I would expect that in this audience, there's going to be a lot of people who've at least done algebra too. If you've done topological data analysis and persistent homology, all the much better, but I'm not going to expect that. Certainly if you've done some work in abstract algebra, modern algebra, that can come in handy with some of the concepts here. Linear algebra is, of course, the most salient when you get into algebraic graph theory. But we're not going to require too much graph theory for everyone. Hopefully we're making that more accessible through some simple coding. The audience here, primarily we're looking at people who are working in Python, need to do work with graphs. Maybe you have a data science role or a data engineering role. This is also very applicable for people who come from more of a business role and want to understand the use cases and get some hands-on experience. And this is particularly playing out in terms of data strategy and some of the path forward on AI. We'll touch on some of the subjects. As far as key takeaways, definitely ESIP has the notion of let's give at least 3 key takeaways from each workshop. And so I will leave that up to the group to decide really what is coming out of this discussion. But a lot of the goal here is to give hands-on experience with the popular open source libraries and really cut down the learning curves. So that's what, if anything, KGLib is a lot about, cutting down the learning curves so that you can go out and use these disparate technologies together. And definitely there are coding examples that have been used as starting points for other projects. And we'll talk a little bit more about kind of the longer view. How do you take these technologies and scale them out on things like Spark or Ray or Rapids, Dask, other kinds of frameworks that allow for much larger scale? Okay, so for anybody who's just joining, if you look in the chat, there will be links to this open source project here. If you want to go ahead and set up KG Lab locally, should just be through a pip install or conda install. And there's also documentation that's linked in that repo, but here's the docs for it. I'm going to cut over to doing a real brief 15-minute introduction to what we're talking about here. And I guess first off, just as an intro, who am I? I made a mistake of studying something that everybody warned me about. I studied AI in grad school about 40 years ago. And then I did a deep dive in an obscure area that everybody told me was worthless called neural networks. In fact, I used to be CTO for a publicly traded firm that made hardware accelerators for neural networks. And at the time, large industrial giants cared about it, but nobody else. These days, the world has come around to thinking that neural networks might be useful. I also had the misfortune of being a guinea pig for a little project that was later named Amazon AWS. And I used a new open source project, led a team that built out the first large instance of a new open source project running in the cloud called Hadoop. And since then, I've been involved with Apache Spark and Project Jupyter, Ray project, and some other open source spacey things like that. At least as a contrib on a lot of those, but also doing tutorials and being involved with conferences and whatnot. So let's get to the heart of some of this. Okay, so I want to introduce a notion called graph thinking. And actually just kind of real brief, I don't even know if I can see it here, but at least I can watch the chat. Real brief show of hands. Gosh, I'm actually presenting full screen, so I can't see chat. I hope that some folks here have at least been exposed to the notion of some of the cognitive frameworks that we talk about in computing. There was a really excellent discussion, actually a number of excellent discussions yesterday in the tribute and memorial for Peter Fox in terms of, there was a breakout session about framework thinking. And framework in the context, I believe, what Peter was talking about was as, say, McKinsey would use it, or some of the large consultancies tend to talk about cognitive frameworks about approaching a hard problem. And the phenomenology that you go through, the process that you go through in terms of trying to understand in a very complex, difficult context. And there's a number of other types of frameworks, if you will, that are used in computing. Certainly there's statistical thinking, if you've never encountered that before. Those of us who had to endure getting statistics degrees, yeah, statistical thinking is a view of the world. And it leads to certain approaches and outcomes. Computational thinking is another view of the world, something that, of course, came out of earlier days at MIT and more recently being used in education at CMU and others. And it's a way of having abstractions where you can work towards solving problems with compute resources. Graph thinking is yet another one of these, and it's a bit different view of the world. And it's what we want to introduce through this workshop. It has trade-offs. Graphs are more complex. And, I will tell you that when it comes to graphs, not only more complex, but a lot of people just sort of run screaming in the opposite direction when they encounter work with graph technologies, and others don't. And so let's describe a little bit about graph thinking and about why is that the case. So first off, a real brief story, but envision that you're somewhere off in the woods. And there's a little village, and it's got a mill, it's got a brewery, it's got a pub. There's some farmers. Let's build out a description of who's in this village. So we've got Pat. Pat works the pub, and Pat has a couple of friends, Hannah and Thomas. And we can start to build out a little bit of a description there of who Pat knows. Now let's expand this. Hannah works the fields, produces grain, and has a friend, Hayden. And Hannah sells grain off to another person here we talked about, Thomas, who works poultry and produces eggs. Thomas is a friend of Brenda. And then we'll take a look at Hayden. Well, Hannah also sells grain to Hayden. Hayden works the mill and produces flour from the mill. Hayden has a friend, Chris. And then Brenda works the brewery, also buys grain from Hannah and produces beer. Brenda sells that beer back to Pat, who runs the pub. And Brenda has a friend, Kim. And then Chris, Hayden's friend Chris, works the bakery, and as such, buys flour from Hayden, buys eggs from Thomas, produces bread, sells that off to Pat. And then Kim works a recyclery, and Kim picks up organic waste from several businesses here, poultry, the mill, bakery, etc., brewery, and then creates fertilizer, sells back to Hannah. And so already here, in the context of just 7 entities, 7 people in this medieval Black Forest village, we've got the notion of a circular economy. So we have people who are producing and consuming, and they do trades with each other. And, the net product is that people can come visit this village and go to the pub. Okay, so this is an idea of a graph representation. And again, it's already getting us some complexity, even though it's only 7 elements. And I see that we have 2 chats right now. And for the life of me with Zoom, I cannot get to, there we go. Ah, yes, okay. Thank you, Doug. Exactly. Well, this is Pattern Agricola. And for what it's worth, I do a lot of work in Europe these days, especially in Germany. And I have some close friends who live not far from the Black Forest. So yeah, we were joking about that village. But here's the problem. If you want to take that data, again, it wasn't that enormous. It's just 7 entities and some links between them. But if you want to represent this in terms of a relational database and do the different normalization forms, here's what you get. So we would end up with 6 tables. If you take this out to 3rd normal form, you would end up with 6 tables, and you've got a little schema there. And the question is this, that if you happen to be an expert in the economics of medieval villages, and somebody were to throw these 6 tables at you, would you be able to perceive any of the nuances of the patterns and the dynamics that are occurring in that village? Because this data has been normalized for database storage and retrieval, and it has been blessed by the gods of relational databases. And I'll throw that out as a question for discussion a little bit later on. But my experience has been that domain experts they really struggle when they're looking at a bunch of foreign keys that are represented as integers, and the connections between the entities that we're trying to represent here just get lost. So that's an important point, is that data representation, there are reasons why we do normalization for relational databases. And a lot of that has to do with fast storage and retrieval, fast query. But that does not necessarily represent the sum total of what we need to use data, how we need to use data. And so graph thinking is much more about how can we leverage patterns, and how can we understand more about relations, actual relations, not normalized relations, particularly in a complex context. So first off, let's acknowledge the complexity of the context. And this is something that, sticking it into a bunch of tables is actually going to obscure the interesting parts. Number 2, identify emergent patterns. And number 3, make informed decisions based off of that kind of analysis of patterns or shape. So geometry comes in actually really useful here. In terms of thinking about patterns, let's focus, for instance, on Hannah. Hannah's relatively new in the village. She'd like to expand her business and, of course, works the fields and produces grains. She's noticed that her customer, Brenda, buys a lot of grain. So how can we go through this data and find out, are there other villagers that are similar to Brenda in terms of their businesses? And if you do a bit of pattern analysis here, if you look at this in terms of a graph, yeah, it turns out that, well, Brenda sells food to Pat and also sells organic waste to Kim and consumes grain from Hannah. Now, Chris similarly sells food to Pat at the pub and also similarly sells organic waste to Kim, but doesn't buy grain directly. So, a natural question there would be, if you're looking for similarity of users here, Chris is relatively similar, according to some metrics. Chris is similar to Brenda and could be a likely candidate to expand the business. What if the bakery could use unmilled grain directly, maybe make sprouts or malt or something like that? And another question would be, let's say Hannah is interested in sponsoring a co-marketing campaign. She wants to drive more demand for grain. Who are the customers of Hannah's grain customers? So second degree. We can take a look and for instance, we could do a breadth first search and we could look at 2 hops away. And it turns out there's, pretty good pickings there. Chris is, again, one of the people who's 2 hops away. Kim is also 2 hops away. Pat is also 2 hops away. Anything that would ostensibly increase their business would also likely produce more demand for Hannah's business. So these are 2 forms here of taking a look at sort of these geometric relations across the graph. In one case, we're looking at similarity. In another case, we're looking at a breadth first search, a couple different algorithms there. Okay, and we can get into some more use cases. Village in the Black Forest. I hope that everybody's still there. I think I just lost video. Hello, video. You can hear me, but yeah, I don't know. The video kind of froze here.
Slides are going okay. So.
Oh, good. Okay, thank you. Good. Great. Okay. Well, let's just say, for instance, if a tech billionaire did use time travel, which businesses are the most from this village? In other words, who would just look at as potential acquisition targets? So if we were to run a graph algorithm such as betweenness centrality, we can see that from our graph back here, we can see that there are some businesses which are more connected, if you will, that have a lot more of a central role in the commerce of this village. Hannah has a centrality measure of 1.83. Chris has a centrality measure of 117. So we can start to do some ranking and start to figure out, okay, which are the real critical parts of this graph and this economy. And another thing, let's say that we have a new kid in town. Mika is an old friend of Kim, moves to the village, happens to have a delicious recipe for chicken sausage that would go quite well at the pub. So as an exercise, can you print out this graph and sketch out, how does Mika fit into this pattern? Where would Mika work? Where would Mika buy from? Where would Mika sell to? And, ostensibly you can see that if we start to add more data, there's a natural fit for working into the relationships that are defined types of relationships as time goes on, as we get more kinds of metadata to work with. Now, I want to jump back a bit and talk a bit about the cognitive theory here. And I'll just throw this out for discussion a little bit later in a moment here. But I am curious if anybody else here has run across Dave Snowden's work on cynefin. Cynefin is a Welsh word. If you speak Gymraeg, it means habitat in Welsh. But the idea is that Snowden was at IBM, at Global Business Services, late 90s, and they were running into a lot of, how should we say, leadership styles amongst their clients. And they noticed that, some leadership styles work better in particular contexts than others. So they wanted a way to describe this, and they came out with Cynefin, which describes 5 contexts. And I'm showing here simple, complicated, complex, chaos, and then the one that's in the midst of all of them, complete disorder. There's primary source if you want to check it out. There's an article they wrote some years later for but just to talk through this, simplest is the known knowns. Sorry, there we go, lag. There's a simple context of known knowns, and this is where you have a stable situation. You have clearly defined cause and effect. There really isn't a lot of expertise required so long as you know what the best practices are. You just establish the facts, determine the needs, and follow the rules. And so simple context is, well, a nice thing to have at times. There's the complicated context in Cynefin that Snowden described, where you have known unknowns. And this is where you really require some expert analysis to be able to determine cause and effect. And so leaders must be able to assess the available facts, but then rely on experts to come in and analyze the situation, and then take the appropriate norms, take decisions based on trade-offs. And then there's the infamous unknown unknowns. If you're looking at the dates, Cynefin came out in 1999, and it was quoted just a couple of years later by a gentleman named Rumsfeld. A complex context of unknown unknowns is where, frankly, determining cause and effect is just reductionist methods will not work. There are ways that emergent patterns, though, can be perceived and leveraged to make informed decisions. And so in this case, a leader must be able to probe a situation, sense the emergent patterns, rely on the expert analysis of trying to discern those patterns, and respond accordingly. And typically this requires some experimentation, some tolerance of risk. Failure is something you just have to work into the cost of business. And the thing about it is that these days, whether we're working in research or in business, more and more our environments are quite complex and resemble this more than anything else. There's also the notion of chaos, that is to say crisis. And during crisis, there isn't any knowable cause and effect at play. Instead, you just really have to work toward where there are islands of stability. How can you sort of revert the chaotic back into a complex context to try to reestablish order? There's also the notion of a complete disorder, which Snowden described, but we'll focus on these 4. And part of what they were doing with the Cynefin framework was they were really leveraging, elements of learning theory, pedagogy, or teaching theory, if you will. There's a really interesting book, How Learning Works, by Susan Ambrose and others from 2010 that goes into some good description if you've never run across that. But in terms of like developmental psychology of how do people organize knowledge as they're progressing from just a complete novice in a particular subject to becoming an expert. And we can represent knowledge acquisition through these stages of expertise by using graphs as well. And that's in fact what Ambrose and others do. So I've tried to represent that over on the right-hand side here. In terms of novice learners typically have not acquired enough of foundation or basis in a subject. So they're working with initially sparse mental structures, superficial mental structures, usually an unconnected set of simple facts until they start to understand the definitions and what the relationships are. This kind of cognition, it's typically more context-free use of features and rules, not a lot of cause and effect or responsibility for consequences. Really will struggle if they're presented with uncertainty in the data. So you want to simplify things so that people can pick up when they're first struggling with a new topic. As people become more advanced, they tend to make more associations. This can be visualized as, say, sparse links between the facts. The facts are becoming more connected. You get more sophisticated use of rules, more situational analysis, and is typically more of like a sequential analysis through information using techniques such as association. And this is where, people start to begin to probe and ask questions. As people become more competent practitioners in the field, they tend to leverage more hierarchical process for organizing the knowledge that they've acquired. This is commonly visualized as decision trees, and at this stage, a learner can really formulate plans for other people to take action. So there's a lot of analysis that's going on here. But then as you get into more expert levels of a subject, people understand how to break the rules. And where is it the rules just don't fit? Understanding the exceptions to the rules means that instead of a decision tree, you're working with a graph. And so the sense making, as people become experts in the field, tends to leverage more emergent patterns. And this is something that, in pedagogy, and all of us who've ever worked as professors, we've had to grapple with learning plans and lesson notes and all the rest. But this is something that the psychologists know quite well. And so you can kind of see that there are these parallels between having a simple kind of context and the notion of how novices approach a new subject versus going out into, say, a complex understanding, leveraging emergent patterns of how experts work. And if you align these, you basically come out with, novices working with simple queries, practitioners working with analysis and planning, more complicated, and graph patterns being what happens when people get to more of an expert level. And I'm not going to go through a lot of detail here, but there was an article that we talked about, sense and scalability, that was listed in the notes for the workshop, if you want to check it out. And I did this work with Jürgen Mueller out of BSF. But the idea is, if you track through the histories of data management frameworks, and I've authored a small mini book called 50 Years of Data Management, but I'll also reference a book by a couple of my friends and colleagues, Denise Gosnell and Matthias Brockler from DataStax, where they had a chapter called Graph Thinking, and we reference it in the article here, Sense and Scalability. If you look at the history of data management and you roll back to 1970, when Edgar Codd proposed relational projections and what eventually became relational databases in SQL, they were struggling with a relatively simple context. They had people who were overcomplicating the code. They were writing in COBOL, working with systems like IMS and Codicil, whatnot. And so they wanted to be able to make programmers' time more efficient. And they wanted to simplify data management. So they came up with relational databases. And these were really good for two things. One is businesses could hire people who were less expert at computation. They had guardrails. They had bumpers. You can think of like taking kids to a bowling alley where they put the bumpers up. So they had guardrails where they could get less expert people working with data and have less disasters. So that was a lot of a hiring strategy. But also, if you look at the first area outside of the intelligence community where relational databases first took off, was in finance. And I'm saying this because I used to work for a gentleman who led relational databases at IBM back then. The driving motivation for a lot of early sales from relational database was in finance. And the thing is, in finance, if you're a VP of technology, you work in IT as an executive at a bank. Well, the bank's priority is that they get their reporting out, that they stay within compliance. That's one of their big priorities. If you're a VP in that role, your bonus is predicated on making those reports in time. And so you have to compute those. If you have a relational system, you can get guarantees for certain classes of computation on both the read and write times. And so you can project out for a given report at a given scale how much compute resources are required. And therefore, you can hit the deadline and you can make your bonus. If you're a bank VP, those bonuses these days are 7 figures. So it's a big deal. And you're willing to spend a lot of money on data management systems that will make sure that you make your bonus. And frankly, that was how relational rolled out in the industry. It's because there's a lot more guarantees and a lot more guardrails. But the problem is, it obscures the fact that if you really do have to dig into complex patterns, there are things that relational doesn't allow. And that's where we get into the graph technologies. And that's both a plus and a minus. On the one hand, it allows us a lot more capabilities, but on the other hand, it does present a lot more complex kind of computation. And you can get into situations where you have something that at small scale, the computational complexity of what you have to accomplish, yeah, it has a quadratic term and it has a cubic term, but if you're only running 1,000 elements, nobody sees it. But when you get up to 1 billion elements, suddenly a job that maybe should have taken a few minutes is taking 3 weeks to compute. And you literally see these in industry. So working with graphs brings risks. You kind of have to know what you're doing, and you need to rely on some good libraries for that. So at that point, I have introduced some of the elements of discussion. Let me cut back to, I'll stop share. And let's take a look at chat. Okay, yeah, Rumsfeld, exactly. Thank you, Doug. Okay, great. Thank you, Ryan. Glad to hear about some. So let me just ask that as a general question. Have people here run across Kinevin before? Or should I say that introduction to Ambrose and some of the ideas out of pedagogy, is that coming out of the blue? No. Okay, good. And what, okay, great. Thank you, Ryan. You had something, what is emerging? I'll take a look at that URL. Okay, good. I'll check out this article later. Okay, so let me open up just real quick for Q&A. As far as graph thinking and what we're trying to present here is that we are trying to move beyond relatively simple frameworks for data. Arguably, you can say that relational databases handle a simple context, whereas, say, a data warehouse with business intelligence, data science over the top of it, OLAP kinds of things, that's much more of a complicated context. Whereas what we're talking about here is getting into much more complex contexts. And certainly when you look in business, for instance, I mentioned working with folks in Europe that run very large chemical factories, but they're also very concerned about sustainability because number one, they are an enormous consumer of energy. And number two, they're operating within Europe, which has very, very tough standards for compliance. And then number three, their business is recycling waste materials in a lot of ways. They, for instance, they have large factories that recycle electric vehicle batteries. So the idea is that these days we see much more complex business contexts where oversimplifying the problem, and particularly oversimplifying the data, can actually not just lead to risk, but in some cases can lead to disaster. And I can give examples of that, but this is the message that we're trying to convey. Okay, great. So Ryan has a question. What advice would you give for learning how to think about computational complexity in terms of what you're trying to accomplish? Yeah, okay, good question, Ryan, about computational complexity. And I do have some resources there. I think that I linked those. Let me dig up. There was a really nice computational. Sorry, I was trying to dig some. Okay, computational complexity. Well, there's a couple of things there. On the one hand, there's certainly the order n statistics that we use in computer science to try to describe the algorithmic complexity. So, when we're talking about, we have an algorithm for doing traversal on a graph, and we know that it's going to have some different terms in terms of its cost, its complexity. And we know that, the larger coefficients are on the terms with smaller exponents, let's put it that way. But there are some terms out there that are quadratic or cubic, and we just can't get around that. If you're dealing with numbers of a graph, the scale of a graph that it'll all fit in memory, well, you can probably get away with it. But once you start trying to scale out and distribute, then you can run into some real big problems. So for instance, there are some very popular graph databases. I don't want to mention too many names commercially, but the most popular one started out as using Cypher, being able to run on a laptop or a single node and do some interesting work. It was never written for scale. The company, as it's grown in popularity, has been selling commercial licenses for scale. No, not Neptune. I'm talking about Neo4j. They were never really written for scale. They were never known for being able to do scale out. They've been selling an enterprise version and bragging a lot about scale, but when you dig into the particulars, um, it just doesn't work. Oh, right. Yeah, exactly. So Doug had a point about Neptune. Yeah, Amazon has AWS has Neptune service, which is actually quite good. And when you look at the large industry use cases of graph databases, Neptune comes up over and over again because it's kind of becoming a go-to solution. There's also Tiger Graph and Anzo, and well, there's a whole bunch of these. Frankly, I've been tracking the graph database vendors, and there are over 30 vendors in that field right now. None of them are feature complete. So for instance, if you want to be doing a labeled property graph and doing some really complex algorithm work on your data, well, that's one thing. If you want to be doing semantic technologies, and that's another. So for instance, Anzo and Neptune both provide ways of doing labeled property graphs, but also doing semantic graphs. But they're not so good at doing both labeled property graph and semantic work on the same graph. You kind of have to choose one or the other. So the idea of having latent bindings for your semantics is there. Yeah, and Ryan, thank you very much. So Gartner had a report, and yeah, that's really good. I'll reference that actually in the next section here real quick. But Gartner did an about face in February. Even the middle of last year, Gartner was saying that graph technologies were entering the trough of disillusionment. And then in February, they came out and they said, okay, we changed our mind. Graph technologies, graph analytics are at 10% penetration in industry in 2021. We project over 80% penetration by 2025. It's going to become a game changer. Exactly. Yeah, that's the one I'll point to. So yeah, and if you look, so for what it's worth, I'm on the program committee for two of the largest graph conferences, both for Connected Data World and for Knowledge Graph Conference. And I do a lot of work in the conference space for other AI conferences. And it's really interesting because if you look at all the tech majors, they're all out there bragging about their enormous graph projects. As far as operational details, they stopped publishing those in 2016. And I mean, you can literally look at like Facebook with their support of Apache Giraffe and other things. They would talk about what they were doing, or rather, they would talk about how they're doing it up until 2016. And then everybody just completely put a lid on it. Amazon now is out there talking about product graph at trillion entity scale. Believe me, you will never get any details from them as far as operationally, what are they doing, even what kind of libraries are they using. The most disclosure that we get are, for instance, out of Alibaba and Ant Financial out of China, using things like Geobase. And there's a couple of projects over there coming out of China where they do get more operational details. But the tech majors are basically seeing graph work as secret sauce. And more and more industry is popping up with really large use cases. You see some really fascinating work at Siemens, Novartis, Refinitiv, a lot of different verticals. Finance has certainly become really important as far as like KYC. Question from Valerie: are there good methods to identify stale relationships in large complex graphs? Worried about long-term maintenance? Yeah, it's a great question. We're going to look at something called Shackle, which is a way of being able to measure and essentially assert rules and use those rules almost like you would think of unit tests, but unit tests on your graph data. And so, yes, we can make assertions about what we believe to be the norms within a graph, and then run Shackle and find out, okay, what rejects that hypothesis, and therefore we should take a look at those relationships because they don't seem to fit what we know about it. There are also techniques that we'll look at here today in terms of probabilistic methods. So for instance, we're going to look at one area of statistical relational learning. It's called PSL. It's Liscator and company out of Santa Cruz, UC Santa Cruz, doing probabilistic graphs with conical optimization using hinge loss. And so we can basically assert rules for what we believe to be the case within a graph, and then find out, okay, what violates those rules probabilistically, what kind of truthiness is there for a given entity, for a given relationship, for a subgraph, et cetera. Do we believe it? And I think this is super important in terms of assessing data quality in very complex contexts. Okay, a little bit of discussion Thank you for that. And we'll have more of that, but I'm not sure exactly what I'm seeing on my Zoom controls here, but I will try to go back. Screen share. Okay. Let's see if I'm actually sharing my screen. Good. And then I'm sharing all kinds of things. Okay, great. Okay, let's go back and step through a couple other sections. One is I just want to introduce real quick. So we have this library KG Lab, and there's a lot of resources. We'll be looking through this. The reason why we're doing it is because there have been a number of different popular libraries and also commercial products, but in different areas. Again, it's kind of balkanized. There's a lot of different camps. And we wanted to have something that could leverage better principles of functional programming, distributed systems, hardware accelerators, et cetera, using the math, really. We wanted to be able to integrate from these different camps and also parallelize better. And so, we've done integrations. I think everything that's shown here on this little ring, we definitely have integration paths for already, and there's definitely much more planned from a landscape diagram. There's a lot of areas here. This is all in the documentation if you want to check it out in more detail, kind of more minutia though. Now, I do want to make a little bit of the business case. I believe Brian was bringing up about the Gartner report. Certainly when you talk about data, most people immediately go to thinking about tables and this idea of sort of data composed in rectangles, rows and columns, grids. And we think about this in terms of SQL reporting, in terms of spreadsheets, talk about tables, except that under the hood, they aren't. When you're working with a spreadsheet, there's a dependency graph. When you're working with SQL queries, you've got DAGs in terms of the execution graph, the query plan. And the thing about it is that by using this kind of spreadsheet interface or SQL, you're sort of sweeping the complexity of the graph under the rug. And the metadata and the business rules in particular, these are internal aspects that get obscured. And boy, if you ever want an earful about that, check out Felina Hermans. She's a professor at Delft. She did her PhD on tech debt in Excel spreadsheets. And it's terrifying when you look at the financial reporting of the Global 2000, 95% of that, the last mile is done in Excel. And as far as understanding the business rules of how those CFOs are working, it's all hidden inside of a spreadsheet somewhere. And believe me, it changes from quarter to quarter. So as far as accountability, it's not there and it's terrifying. And that's why we end up with things like 2009 crisis. Sweeping the metadata and the business rules under the rug might be a bad idea if you're in a complex business environment. And this is what Gartner has come out. Again, they reversed their opinion of graphs in mid-February. Knowledge graphs can form a key component of data fabrics by exposing metadata and business rules, enabling data scientists to quickly identify and use data they need while preserving context, representing all forms of data in a standard queryable format. And 50% of Gartner inquiries about AI are now some discussion, some part of it is about graph technology. So the thing that spreadsheets and databases tend to obscure, which lead to tech debt, that's exactly what graph technologies are allowing to come to the surface, and we can operate on that. I am involved with doing industry reports. My colleague Ben Lorick and I do a lot of surveys and reports, analysis. We have a recent one from last year about NLP adoption. We have a new version of this in progress right now. But we found that in industry, the top 4 usage for NLP is actually preparing graph work. So it's really, really resonant. And certainly we see use cases across different verticals, a lot of different areas. Certainly healthcare or life sciences is an area where this is very becoming very pronounced, certainly also in finance as well, but definitely also in manufacturing. And frankly, I want to say something that, everybody talks about the tech giants. And when you say the word knowledge graph, immediately people say, well, Google did that. The fact is, if you go to some of these large manufacturers, their graph data, one use case at a graph data at a manufacturer like BASF or Siemens, one individual use case will be larger than the entirety of Google Knowledge Graph. So I want to say that again, you take some tech giant that's well recognized in this field for AI, and you talk about their immense work in graph data, and Google's knowledge graph being kind of a reference for that. Simply one out of many use cases at a manufacturing firm will be larger than what Google's working with. And that trend is probably going to increase as time goes forward, if you think about where the data sources are and what the implications are, especially when talking about factories and a lot of geospatial data that they're working with. It gets really interesting. Okay, the other thing before I head to questions here, let's see, I don't think, I'm not going to spend too much time on this. Just one thing. There's some primary sources if you want to dig down about the history of knowledge graph, even going back to Charles Peirce back in the 19th century. What I will point to, though, is when we have these discussions about AI, these days, everybody wants to talk about deep learning. And like I say, I have many years of working with neural networks. Deep learning is super useful. It's not everything. And there are marginal returns on larger and larger deep learning models. And Neil Thompson at MIT and his team have definitely articulated that quite well. I like their monograph, especially. A friend of mine, another colleague, I should say, a boss of a friend of mine, Uli Sadler at U of M, had a really great talk last year at one of the academic conferences that we have in this field, talking about the need to mix machine learning models with graph approaches, because graph approaches really bring in the domain expertise and the complexities of what the domain experts understand. And so that's a lot of what we're heading toward with graph work. I'm not going to dwell on this too much, but self-supervised learning is a good example of where you would combine sort of the best of both worlds, whether you're working with predictive analytics with machine learning, or whether you're leveraging domain expertise that's represented in a graph. And certainly we're seeing this in the emerging area of data governance in terms of the current generation of metadata management that we're seeing out of Amundsen and Data Hub and Marquez and others. This area is really growing for graph as far as the tech industry is concerned. And that sort of dovetails into a lot of the discussions, if you've been following, about data mesh. And a friend of mine, Zhamak Dehghani and others have been talking about. So I've listed some resources here from Joe Hellerstein at Berkeley, Zhamak Dehghani, of course, who created data mesh. Also Sam Ramji, really great podcaster and chief strategy officer at DataStax. Okay, that's a little bit of background. I've got a little bit of graph theory, but let me try to get into some questions here. Okay, I'm curious if we can use graphs to manage relationships within keyword vocabularies and ontologies. Great. So Tyler and Kate, excellent question. Yes, actually, so we will show some of that. In the W3C side of the world, the semantic technology side of the world, there is something called SCAs for being able to represent, again, taxonomies, sort of weaving an ontology through your semantic representation. Yes, the relationships within keyword vocabularies is very important. Heather Hedden is one of the experts that I go to, and I recommend. She's one of the experts in teaching about taxonomy, especially. But we'll show some examples of that, and also about how to measure it. Miranda, have you ever worked on creating graphs of metadata in data sets? Yes, definitely, to see the connections between data sets. So for what it's worth, I got introduced to ESIP at the 2020 winter meeting. I gave a keynote about using knowledge graphs to represent metadata of data sets. It was some work in progress that I was doing through NYU and the White House on behalf of USDA and others. Yeah, we can talk much more about that. And Luis had a question: of vocabulary expressed in RDF, OWL is a graph. Yes, very much so. RDF is a form of representing graphs with more strong guarantees about the semantic representation. OWL expresses more about what you can do with the inference over the top of that, and how to express relationships more fluidly. There's a number of these kinds of RDFA and SCAs and other technologies that build on each other, Shackle being one of the more recent ones, kind of at a higher level as well. Ryan had a thing, another good resource on the background definition trends of KGs. Oh, good. Thanks. Thank you, Ryan. Doug Newman, NASA, USDS is producing graph for dataset metadata. Great. Okay. Yeah, definitely. I mean, there are working groups within ESIP that are, of course, concerned about graphs in a number of different aspects, whether we're talking about ontology development or harmonization of semantic technologies, whether we're talking about what's going on with developing knowledge graphs, really sophisticated work at NASA and NOAA, USGS, and others. Great. Okay, good. I'm glad we're getting some good discussion. What I mean to say is there's a lot of great resources inside ESIP and a lot of really excellent practitioners in this space. Okay, and so definitely, thanks, Doug. Great to see that there too. Let me talk real brief about a little bit of the math, just enough of the math. Okay, so, and this is important because we're kind of at a crux of how do we use the math or not. So in algebraic graph theory, we have the notion of transforms between graphs and algebraic objects. So examples of algebraic objects include vectors, matrices, tensors. If you want to go beyond tensors, you can get into some really bizarre stuff like circulants. But the idea is that we can represent graphs to some degree, to some dimensionality, by using these different types of algebraic objects. And typically we can have some transforms and inverse transforms to go back and forth. Now, historically, a lot of the computation has been focused on matrices. And there's really great work with decomposition, factorization. A lot of libraries in the graph space, graph algorithm libraries, are leveraging a sort of non-negative matrix factorization trick. And there are some really excellent resources. I highly recommend David Gleick at Purdue, formerly Stanford, but he's done a lot of really interesting work deconstructing PageRank and different types of graph algorithms, but also looking at really presenting even to a novice audience of how to do decomposition factorization methods on graphs and matrices, talking about QR decomposition and LU updates and down dates and all that. Sort of the grandfather of this area is Tim Davis, now at Texas A&M. And Tim Davis, if you haven't seen, I've got a picture there. Tim runs the Sparse Matrix Museum with some fantastic visualizations in MATLAB for different types of sparse matrices that are actually used as test cases for developing hardware, things like that. But Tim Davis also is one of the main authors of GraphBLAS. And I've got a recent paper that's linked down there. It's a Redis graph using GraphBLAS, and just how they were able to blow away the competition. They were showing orders of magnitude difference in terms of executing graph algorithms at scale when compared with things like Neo4j, TigerGraph, and others. And again, they're using a lot of interesting factorization methods under the hood. Wait, quick, there's some chats there. Maybe I just can't get my mouse. Zoom is playing havoc with my mouse. I'll come back to chats in a moment. The point I want to make, though, is that the matrix factorization methods, like we talked about here, while they are very useful, they have some drawbacks. One is they are very numeric, so you have to transform your data into a numeric space, typically use these. Of course, this is very useful for graph algorithms, for visualization. Deep learning requires this, etc. But other types of work with graphs really require a symbolic representation. So certainly when you're working with natural language, when you're working with compliance audits, any sort of human in the loop, trying to represent domain expertise as rules, when you're working with explainability, different areas of accountability, these all require symbolic representation. So it can't just be numbers stuck in a matrix. So you have to have ways to go back and forth. Also, there's the small matter of hardware, because again, a lot of graph work is very computationally expensive. And so as sort of a sub theme here, I have another set of talks. Recently did a mini book with NVIDIA, but one of the big concepts there is what we call thinking sparse and dense. There's a couple of ways to look at graphs. One is in a sparse sense, very symbolic. And certainly RDF and OWL and the other semantic technologies really take this view. And in machine learning in general, when we're working with data science workflows, the early stages tend to be more sparse. This is where you're doing your data preparation and start to do aggregations. And these are typically bandwidth limited. Even if you're digging into the internals of a deep learning solution, you'll see that there are sparse elements in terms of calculating a loss function. That's bandwidth limited, it's not compute limited. And sparse, this is where the business people, the stakeholders, this is what they recognize. So even if you do your number crunching numerically, you need to get back into the sparse realm before the stakeholders understand it. But then there's also dense work. And so if you're looking at a machine learning workflow pipeline, typically when you're in the training stages, you're doing more dense work. You take your features and represent them in vectorized form. These are typically more compute limited kinds of approaches. If you're working, for instance, in deep learning, these would be the convolution layers, stuff that's readily vectorized and run on things like GPUs. So there's a book about this, or a small book, Dean Wampler and I recently released, working with the open source leads in machine learning at NVIDIA. And it's a free download if you want, but we really explore software patterns to really let the hardware optimize as best as it can, and what the implications are on software engineering process, particularly for data science. And one of these that's really important for us is this notion of when you have a graph, there are times when you need to work in sparse versus dense. There are times you need to work in something that's more symbolic or something that's more numeric. But what you really need are to have reliable, tested ways of transforms and inverse transforms, so that we can take your graph data and project it out into something that can be used elsewhere. So if you do have your graph in RDF, and you're working with RDF and OWL and SCAs and these kinds of things, that's great. We can do a lot there. But if we want to do work with, say, network X with some sort of graph algorithms, we need to be able to transform an RDF graph into what can be represented down here for iGraph or network X. Or maybe we need to represent it as a tensor and run it through PyTorch. So this is where a little bit of the math comes in handy. And it's also, if it's nice to use a standard library, because if you just have to rewrite this code every time, you tend to get a lot of bugs there. It's also where you can really take advantage of the hardware. And I want to talk about how central that is for data science. A lot of what we do in data science is to manage dimensionality. So we're generally going through this process of having a lot of unstructured data as our sources and moving from relatively unstructured to more structured. And so managing dimensionality, it's an essential part of that kind of trade-off between where do we use symbolic or numeric representation. So we usually start out with the symbolic, sparse, unstructured data, and then we work with it to identify where can we find low order embeddings, and then we iterate, test, and refine that, and work that into features where we can establish some kind of dimensions for machine learning, and then from there train models, evaluate them, etc. So managing dimensionality and what we're doing with like sparse and dense and symbolic and numeric, it's very, very key to data science in general. And that's kind of the thesis of graph data science, I guess we'd say. Okay. So having introduced that, let me check chat and see, and then we'll cut over into some code. Great. So there's some discussion. NCAP, NCI. Great. Thank you, Ryan. Okay, Ryan had a question. Working on this for space science applications. Oh, great. Okay, good. Good networking. Glad to hear. At this point, I would like to cut over into some code, get away from the slides for a moment. So I will go back to using this repo, and I've already loaded it up here. I'm running it on my laptop. So if you do a git clone and pull down the repo, then and do an install there. We've got a bunch of notebooks under the subdirectory called examples, but just from the top level, sorry. First off, I should ask, can everybody see my screen okay? Do I need to change the point size or anything? And if I can boost it. It's good. Okay, thanks, Robert. Okay, thanks, Doug. So what I'm going to do is launch Jupyter -lab. Just from the top level inside the KG Lab repo, I'm going to launch Jupyter Lab. And that'll give me some warnings, blah, blah, blah. Should fire up here. Good. Okay, great. And that'll pop up in the browser. It should automatically, oh, come on, my browser is laggy. It should automatically pop up in your browser. If it doesn't, it'll pop up on a host port, probably 8888. Great. Thank you, Luis. All right. So at the top level, you'll see you've got the repo that we were talking about. If you go to the examples subdirectory, double click on that. Under examples, there's a number of different IPython notebooks and some temporary files that are being generated by them. I'm going to start out by showing a little bit of data that we're working with, just real quick. We're going to show a progressive example here. We're going to show some graph techniques that are being applied to the same data over and over. The data itself, if you want to take a look, it comes from food.com. There's the Kaggle competition, and there's a Kaggle data set that has recipes from food.com. There's about 250,000 recipes. So yeah, it's like 200, I think it was like 230,000 entities in it. So it's a significant graph. It's a CSV file. If you want to take a look at the raw CSV file, we've done a little bit of pre-processing on it, so that it's a little bit easier to work with. The raw data was a little messy. Oh, good. Okay, Ryan was asking the link to launch Jupyter Hub. So good point there, Ryan. Yeah, I'm not running Jupyter Hub per se. You should be able to run this on Colab or other places, but we're working with this repo, KG Lab, and if you do a git clone and bring it down, have that on your laptop, then you should be able to run Jupyter Lab. So I was using Jupyter Lab instead of Jupyter Hub. So just showing how to run it locally. And I'll be stepping through all the code if anybody has any troubles with installations. I know that PyTorch and some of the other tools, Apple has become less friendly toward them. So installation hopefully runs well. But if not, I'll be showing everything. Anywho, we've got a bunch of recipes, and recipes have ingredients. And some of the ingredients are shared amongst other recipes. And frankly, there's a lot of overlap in recipes. So you end up with a graph in a pretty big hurt. So I'm just going to show that as like where we got the data from. You don't really need to do any work with it. But in example 1, let's run through this. So let's show how to take a CSV file and build it into a graph using RDF. And this is using a library called RDFlib, very popular in Python for working with RDF. So if I want to go from just standard RDFlib, I would say import RDFlib. I would instantiate a graph. That's my variable G. And now I can add triples. So the construction of a graph is you have a subject that links through a predicate to an object. So that's 2 nodes with an arc between them, an edge between them. So you end up with these structures of subject, predicate, object. We call these triples. And so in an RDF statement, you'll have triples. It can get more complex than that, but that's the general theme. So here, let's define a URL for a recipe. And this is a recipe. I'll show it here. I can even show some pictures of making this recipe. But it's a recipe for anytime crepes. Certainly in my family, we have some crepe recipes we tend to use. I like to make crepes for my daughters. It's a real simple one. This is super simple, really just like 3 ingredients. And frankly, I like to make crepes using beer and whatnot. But anyway, we've got a simple recipe, and we've got its identifier, persistent identifier out there on food.com. So we can create a subject node in RDFlib to wrap that URL. And now we can import a namespace. So there's a kind of vocabulary that is RDF. And we can leverage some predicates from that. So what we're going to do is use RDF type that establishes an ISA relationship. So we can say, let's bring this in. And then one other term, we'll talk about something called namespaces. That is to say, different vocabularies, standard metadata vocabularies, have been developed, and throughout, use in semantic web technologies, there's a number of these. We want to be able to manage these fluently, so we're going to create something called a namespace manager, and then from there, I'll show how we can use it. So we create this variable nm, and from there we can go out and say, okay, I have a URL, and it goes out to something from Foodon, a food ontology. And we've actually had some of the authors of this speak at ESIP. But here's an RDF OWL ontology about recipes and ingredients. So what I'm going to do is make a URL to reference that, and then I'm going to wrap that as a namespace. And then I'm going to look at one of the particular vocabularies there, WTM, what to make, is a recipe ontology. I'm going to bind it with a prefix one, WTM, so I can reference it by just saying WTM colon. And now I'm going to dig up a recipe object, if you will, a recipe class out of that ontology. So now I can put all these elements together. I can use RDFlib to say, okay, add a triple to my graph. The subject is crepes recipe. The predicate is RDF ISA type. And the object is, it's a recipe. So I have, by doing this now, I've established a graph that says anytime crepes is known as a recipe. And now I can add properties to it. We know that anytime crepes takes about 8 minutes to prepare, give or take. So we'll add cook time as a predicate, and then we'll describe that using another vocabulary, XSD, to say it's an integer. And we add that triple, boom. So now we've got some pretty well-defined data, and we can add more. We can say there are 3 ingredients to crepes. There's eggs, milk, and flour. Let's create those. Those happen to be in our vocabulary, so we'll just reference those. And now let's take a look at the graph. Boom. So here is RDF to describe a graph of that one recipe. And it's a bit verbose, a little hard to read. Let's try and do that a little bit differently. In working with RDF, there are a number of different kinds of serialization formats. There's XML, there's sort of the raw RDF like you've just seen here. There's another format called Turtle, which is much more human readable. We reference it as TTL. So if I can come in here and I can say serialize as TTL, print it out, and you get a turtle representation for that recipe. It's a bit more readable. If I want to, I can take and save that as a file. So boom, I've just created temp.turtle, which should be down here. And that should look a lot like what we just printed out. Good. Now, there are other serialization formats. There's something called JSON-LD, which is very popular. And in some ways, it's more machine readable, if you will. It's easier to parse than Turtle, certainly, if you're writing a parser. And you can read it with any JSON library, frankly. So here, we'll write out RDF as, okay, we'll write temp.jsonld. Okay, and so there's the same graph, same RDF represented as JSON-LD. And so I just want to show that, just working with raw RFD lib, you can start to build a graph. Let's take a look a little bit deeper though. Let's leverage KGLab. So KGLab, again, is an abstraction layer doing a lot of integration and testing between these different libraries. So if we want to work with the same data, represent the same graph, with KGLab, what we say is import KGLab, define the namespace. Here are the vocabularies that we intend to work with, and we know what their prefixes are. And then we'll create a knowledge graph instance, and we'll say, okay, here's the name, here's the namespaces. It's now variable KG. And then let's go in here and we'll say, okay, let's create a node, a subject node, our recipe for anytime crepes. And we'll add its is a relationship there. Say it's a recipe. It's cook time, 8 minutes, and then three ingredients. Boom. And if you iterate through, it should be the same exact RDF that we saw before. If you take and save it out, again, we can print it out, but a lot simpler in terms of the Python required. We can save it out as turtle. We can save it as XML if you want to take a look at XML. Somewhere there. Where is my XML? Huh. Oh, sorry, Zoom is obscuring it. All right, XML is a little bit more verbose. We can save it as JSON LD. Now, what I wanted to do is something that's not popular when you talk to the semantic web people, but there's a format called Parquet. And when we work with big data systems like Spark and Kafka and these kind of things, Parquet is a very popular format. It's what's called columnar storage. And it supports things like dictionary compression and predicate pushdown. Long story short, it's very efficient storage for writing, but it's also extremely efficient for reading really large data sets. And it encapsulates a lot of the metadata. And then when you go to use a partition of a file, depending on the queries that you're using, your data frameworks can be very smart and say, hey, I've got 1,000 rows, sorry, I've got 1,000 columns in my Parquet file, but I only need 3 of them. Here are the 3, only decompress those 3. And so you can get a lot of efficiencies when you're using systems like Apache Iceberg or Trino or all those, Spark and others, by using Parquet. So as it turns out, Parquet is actually much more efficient at scale than any of the other serialization formats for representing graph data. And so what we did was to build out a way of translating very quickly, just a couple of lines of Python. You can go from RDF or XML or JSON LD into Parquet. And this is a really trivial graph. It's very small. If I take a look at all 4 of these formats, it turns out Parquet is actually larger. But as the graph grows, the Parquet file relatively shrinks, and also the processing time is order of magnitude more efficient. We'll look at that a bit later. But anyway, I did want to represent that now we have ways of working with tooling, big data tooling like Parquet, working with tools like pandas, data frames, etc. Okay, exercise 2. Let's take this a little bit further. Let's build up a graph that has a little bit more substance to it. Wait, there's one item in the chat. From Miranda, can you import a graph you've already constructed and edit that in KGLab, such as importing XML, Turtle, and adding nodes? Absolutely. And in fact, we'll show a lot of examples of that. But the nice thing with KGLab is you can import from a variety of different formats. And as you're assembling a graph, these are all additive. So essentially, you could start out with a base set of vocabularies in RDF and OWL and whatnot, bring in some CSV data, convert it into RDF, bring in some other JSON LD or XML files, bring them all together into one combined graph, and then begin editing it. Maybe you add some annotations, maybe you delete some nodes, etc., based on graph algorithm analysis. So certainly this is sort of a programmatic workbench, if you will, for being able to edit graphs from a lot of different sources. Awesome. And I can talk about other tools too, if you want to get more visual kinds of tools over the top of this. Graphistry is something that works really well in conjunction with KGLab. Okay, so I'm going to use example 2.0 notebook, and we're going to take a CSV file. Again, we're just going to build out here. We've got our food recipes and ingredients vocabularies. We're also going to include something called SCAs, which is used for defining taxonomies. Okay, and so, one of the things that KGLab has is you can describe the namespace. If you can see, there's a bunch of built-in additions to the namespaces. Certainly RDF and OWL and RDFS, those are all there by default. XSD, these are all very foundational. We throw in schema.org, we throw in Prov, Dublin Core. These are all, they just get used so much over and over. It's kind of, they're part of the default. You can override those if you want, but they don't really cost much just to add them. And then next up, let's define here kind of a translation table. We'll say that we've got some ingredients that we see over and over. So we'll create a mapping here from the text labels for these ingredients to their actual RDF representation as nodes. So, things like water, salt, basil, butter, milk, real common ingredients. Great. And so this is where natural language really comes into graphs. What we'll do is first off, we'll read our CSV file of recipes and just read that. Now we've got a pandas data frame to represent it. And now we can go through and iterate. And for each one of these ingredients over here, we'll match it into our lookup table and find out where its node should be in the graph. So this is kind of an entity linking exercise, if you will. And just run through this loop. And now, at this point, we've got a graph that it doesn't have the 250,000 recipes. It has a subset of that. But we've built up a graph. Let's take a look at it. So we're going to use a real quick library here called PyBiz. What we're going to do is, well, here's just kind of a style guide for visualizing. Some of the nodes from the what to make vocabulary will be in orange. The nodes from the food ingredients vocabulary will be in blue. We're going to take our graph and then project it out as a tensor to create a subgraph that we can load into PyBiz right here. And then we're just going to tell it use some physics to do a force atlas representation. Boom. And take a second or two to load up. What that does is it generates some HTML, some JavaScript, so it can literally render a graph as an HTML page. And now if you look, you've got, here's that orange one in the center is a recipe. Obviously, it's the one node that gets referenced by everything else. The dark blue are the ingredients. You see, some of these ingredients are really popular. They're very central. We'll use that term over and over to represent just how important a node in a graph is, how connected it is, the centrality of it. And certainly when you look at things like salt and water, flour, butter, these are very central because they're your ingredients that get used over and over. Some ingredients in this collection, not so much. Garlic, turns out, now that's not my household. Garlic is extremely popular, but not so much in these recipes. Cider vinegar, also, gosh, no, it's extremely popular, but not so much in these recipes. But anyway, just a real quick visualization. It's kind of fun. It's got some physics to it, so you can drag stuff around. You can add flyovers and do a lot with this. If you really want to zoom in and see the gory details, you can do that too. But PyBiz is a really quick way to just see what's in your data. So there we've got a graph. Let's take this a step further and start to understand a little bit of performance issues, though. When we go to serialize data, do the reads and writes, there's some different considerations. So what I'm going to do is just import time, and then I'm going to do a time delta, reading and writing in different formats. So XML, JSON-LD, Parquet, and Turtle. And then let's compare these. And actually, let me run this twice. So I'm going to run the same thing twice just to warm up the libraries. Okay. And what you begin to see here is that the Turtle format is really good for people to be able to read it. It's very human readable, if you will. It's relatively terse in terms of its file size. The write times, though, are kind of high. It's like twice as slow as the next leading contenders, 4 times as much as Parquet, even for not a huge graph. XML is extremely large in terms of representation, not all that readable. Write time is pretty compact for XML. It was sort of built for that, but still not the best. JSON-LD is very machine readable. It's relatively verbose in terms of file size, but its write time is relatively low. But Parquet really shrinks down that file size and also shrinks down the write time. So what I want to say is Parquet is a natural fit for graph data. It's kind of a shame that it's not used more commonly, although the people who are building graph data frameworks from HPC world, from supercomputing, take for instance, Katana Graph, they tend to use things like Parquet. They're native for that. So that's just real quick work, reading and writing files from different formats, building a graph. And Luis, is a comfort break previewed for this session? Yeah, this is a good time for a break. We've been in for an hour and a half now. So let's take a 5-minute break. I will stick around. Are there any questions? Can we have any discussion or so? Any topics I can try to talk about? We'll come back. It's 9:27 Pacific time here. So it's 27 after the hour. Let's take a 5-minute break. We'll come back at 32. Good. Okay. I agree, Kate. Yes, I made some crepes recently, but my daughters devoured them. Actually, we had a 16th birthday party, and we had a request for crepes for breakfast that morning. So we just had a really nice big batch of crepes, and so this is making me hungry too.
Alexander here.
Hi.
Can I ask a question?
Yes, certainly.
So I might have missed it. When you talk about Parquet and the write speed, is there anywhere where actual format of how the graph is stored in Parquet is explained?
Yes, I mean, at least for what we're doing, that's a really good point, is that when you're working with Parquet, you have a lot more freedom. And so you can define what kind of columns are there, compression formats, things like that. And certainly with that freedom comes great responsibility, so to speak. So yeah, you really want some docs for that. So if you go to the docs for KG Lab, we describe that. So Derwent AI docs/KGL, and under technical reference, there's a API docs. And inside here, if I search for Parquet, so the load and store methods for Parquet are listed here, and so what we describe, I thought it was actually, it's in the code we talk about it. You know, that's a good point. We're not.
Oh, this is the best kind of documentation.
Yeah, no, my apologies. I thought that was an API.
No, that's fine.
So
I'm
gonna fix that. So if I go to the code, if I go to KG Lab and look up KG Lab and real quick on Parquet, we actually have it defined out as an enumeration. We've got the Parquet column names. So we use subject, predicate, object as 3 of the columns that are specified. And yeah, you can see how that's built up in order. There are faster ways to do this, but this ends up being pretty quick. You can actually do reads with cuDF. If you're using GPUs, this will leverage the cuDF library to do vectorized loads and stores. And I know Doug is on the call here, and some others. We have been talking with folks at ESEP about extending the Parquet formats so that we can do things like using NQuads and having other annotation, time data, versioning data along with it. And that requires adding other columns to Parquet. So that's something that I had hoped to be able to show before today, but I had some other open source pull requests that were pretty high priority. So to fix some bugs that came up with the patches. So, but we will be adding more to the Parquet format. So optionally, you can work with NQuads if you are working with version graph data. And this goes into a question that we had a little bit earlier. I apologize, I didn't get to it right away. But there was a question earlier about RDF star. And yeah, we're not going to go into a lot of detail, but currently there are a couple of views of the world. One is working with W3C and technologies like RDF and OWL. You can have semantic graphs and leverage inference and just a lot of wonderful things that come out of that side of the stack. Or there's a lot of graph database vendors that work with what's called property graphs, labeled property graphs in particular. and typically much more efficient in terms of processing. There is a standards body that's been working toward a standard that reconciles. So there's something called RDF star, and with it, Sparkle star, that will be able to use a common technology for representing both semantic graphs as well as property graphs. And then there's also something called GQL, which is graph query. And believe me, it's nothing to do with the Facebook GraphQL. It's something separate. It's a standard that's been proposed called GQL. Frankly, it's been in development since 2016, but they're getting closer. I hosted one of the lead authors recently at a conference. And the idea is that not too far from now, we'll be able to have libraries that can represent both the semantic side as well as the property graph side, and be able to query those efficiently, and sort of be able to harmonize between, like I say, there's 30 different vendors out in the graph space, and they're not feature complete. They don't talk with each other very much. So we're looking toward these standards to be able to harmonize across. One of the big things, as you can probably see pretty readily here from work of KG Lab, when we're looking at recipes, let me go back up here. When we're looking at recipes here, okay, so we have a recipe, we have a URL, we have its name, we represent how many minutes it takes to cook, and we talk about what the ingredients are. And so from a recipe to an ingredient, there's a predicate, there's an edge. What we're not representing is how much of that ingredient gets used. Like, is it 1 egg and a cup of flour and like a half cup of milk? We're not representing the edge properties. And in RDF land, with the semantic technologies, it's actually kind of difficult. There are techniques for doing it. There are a few. One of them is called reification. We can come up with much more complicated ways of describing graphs and be able to work in some properties. It becomes a nightmare in practice. And particularly when you want to read it or parse it or query it, it becomes a real nightmare. So this is why people like property graphs, because then they can put other additional metadata on the edges. And unfortunately, with the semantic web, they never really thought of that as being an important thing at first. So we're looking forward to a world probably not too many months from now. RDF lib has some pull requests already for RDF star. And certainly Jenna over in Java land, some of the others are already doing RDF star. It's probably not the end all be all. There's more work required ahead, but RDF star will definitely start to reconcile some of these impedance mismatches. And I apologize. That came up with that came up from the discussion about Parquet. Part of the problem is the serialization formats are all going to change. And one of the things that's nice with Parquet is you can just add other columns. So if you need to add a column to describe what is the property on this edge, okay, then I've got a key and a value. I've got 2 more columns added, no big deal. And so Parquet actually comes up being kind of a lifesaver in that world.
Thank you very much.
Does that help answer the question, Sam?
Oh, yes, thank you.
Awesome. And we're coming back from break now to another question from Joe. Have you tried to store graph data in HD5 and measure the performance? No, I mean, yeah, there's ORC and HD5 and others. I haven't yet. Certainly we can do some trade-offs. The question is, though, integration paths. The thing about Parquet is that it is native for Arrow. So when we're looking at all these systems that are leveraging Arrow for distributed systems, certainly the whole NVIDIA stack, working with Rapids, but also, looking across at what's going on in Spark and Pandas and Dask and all those, the big thing is Arrow. And the idea is having, resilient, remote shared data, shared memory, I should say. And so Arrow, when you look at the comparisons of Arrow especially with zero copy, I was on the phone earlier this week with a researcher at Stanford who's building a very popular tool in the semantic web space. I won't mention names. And I offhandedly mentioned something about orders of magnitude performance increase if they were to switch to Arrow. And the guy called me on the carpet and just basically said he didn't believe me. And then I showed him some graphs of benchmarks, where loading CSV files for a given set was taking thousands of seconds. And then, loading it using Parquet was 3 orders of magnitude more efficient. And we do see this at scale. So the idea of being able to leverage Arrow and have some kind of, parity between these different types of frameworks by having Parquet as sort of a lingua franca, that's what we're really focused on. I would love to see what HD5 and ORC and some of the others can do. I mean, certainly for a given instance, that might be useful. But again, if you're trying to integrate with preparing data, especially streaming data that's coming in out of Spark Streaming or Spark or Kafka or any of these, Pulsar, probably want to have Parquet first. Great question. Alrighty, let me clear out a few tabs here and we'll get back to it. Yeah. Okay, let's go to number 3. Let's talk a little bit more about visualizations. So I've got example 3. If you want to build up a PyViz visualization, here's just the raw PyViz. I'm going to show a really trivial graph. It's got 2 nodes and an edge. Boom. But there's a fair amount of work. And they talk about, well, you've got add node, add edge. You've got to have numeric representation. You can't use RDF graph data directly here. So it's a bit of work to translate. And that's always kind of a bummer. So what we did with KGLab, I already showed running it, but the idea is we use a subgraph. And this is a way to have an integration path toward graph visualization libraries. So I'm going to bring in, temp TTL is a turtle representation for the data we were just working with. We had written out as turtle during our serialization tests. But here's a bunch of recipes. I don't know. We'll measure it a little bit later, but certainly lots and lots of recipes. So I'm going to just load it here. I import KGLab and I load up that turtle. I've created a knowledge graph right there. Now I'm going to come in and translate that back into a subgraph. I'm going to take a subset of it. I'm going to format it more as a tensor, if you will. And because that's what I need to be able to construct a visualization. So I convert it to a subgraph and then I there's a built-in library that will automatically transform from the RDF space, the tensor that we had to represent it. It'll automatically represent it into this numeric index up here. So I can get a one-to-one correspondence between symbolic and numeric. And then, as we showed before, we'll tell it to use some physics to reformat the graph and then write it out as an HTML file that has a bunch of JavaScript embedded. Boom. And you get this kind of graph that we showed before. Boom. Okay. And so I just want to show that yeah, there's a bit of contrast between working with the libraries directly versus using this abstraction layer. We try to simplify it. There's working to do with matplotlib and others. There's work in iGraph. PyViz is pretty general purpose. There's also Gephi. There's Graphistry. There's a bunch of different libraries. We're trying to make that simpler. All right. Now let's cut over here. We'll talk about queries. And I should mention, there are a few different types of queries that are popular for working with graphs. One of them is called Sparkle, and this is sort of the standard for working with W3C semantic web type graphs. So it's a query language for RDF. There's also something called Gremlin. There's a standard called Apache Gremlin and Tinkerpop that goes along with it. And there's a lot of libraries that have adopted more of a programmatic access to graphs. So you can have endpoints and you can basically run remote small programs to query a graph. That's something called Gremlin. There's another one that Neo4j has pioneered that's called Cypher. Neo4j is the most popular graph database. I was talking about them earlier. There's OpenCipher. There's a C++ library that implements the Cypher query language. I recently ran a poll on LinkedIn, and yeah, it was running about 2 to 1. Sparkle is about twice as popular as Cypher, and then Gremlin comes in third. I recently, for a customer, went to look at gateways to bridge queries across these different formats, and there's not a lot. So the long story short is, if you have a database that has implemented the Gremlin programmatic access, you can get bridges from Sparkle. But if you've got a Cypher database, good luck. There's definitely some work with Virtuoso and others where you can have a Cypher representation, and side by side, you can also do most of a Sparkle representation. But good luck trying to build a gateway between Sparkle and Cypher. So long story short, there are 3 different popular methods. Yeah, Gremlin works out being pretty well, although if you do want to be leveraging the semantic technologies, Sparkle has its good graces. And then, as I mentioned, there's 30 different graph database vendors, and some of them have their own unique graph query languages, which adds even more complexity to the problem. I am looking forward to a day of definitely Sparkle Star graph GQL and sort of standards to harmonize these, but that day is not here yet. So let's work with Sparkle. And here I'm going to show just raw RDF, something really, really simple. There's a note. Oh, good. Yeah, good point about Nifty. So I'm going to give a really, really small graph here. There are 3 people. This is using friend of a friend vocabulary. And there are 3 people, Alice, Bob, and Danya. And what we'll do is create a graph in RDF lib. I'm just showing the raw approach, no KGLab. So I'm going to parse this string as RDF, create a graph in RDF lib, and then here's a query. I'm going to query who the people are, what their names are, and their email. And now I'm going to run that query against it in RDF. And boom, you see, I get some results back out. And if I want it in more readable form, rather than just sort of the raw RDF, I can use something called N3, which is sort of a turtle format, if you will, for the triples. That's built into RDF lib. So I can get a little bit more human readable. But if I want to do the same thing, I can use KGLab with a bit more of an abstraction layer. So here we'll show KGLab, we'll import our recipes knowledge graph. And then let's query. Let's take a look at recipes that have eggs and see what kind of cook times do they have. This is a little bit of a data quality example. And so now I've done a Sparkle query on my recipe graph, and I can do a visualization. I can tie it in. Boom. So for instance, here you can take a look and visualize the query using PyViz if you want to try to understand what the query looks like. For complex queries, that can come in handy. But now let's actually run this query. And as a result, we'll get a pandas data frame. So that's a bit of a nicety. It's a nice abstraction and convenience. So we go from RDF data, we run a Sparkle query, we can get a visualization and a pandas data frame. And if you look at the pandas data frame, we can notice some really interesting things. Some of these recipes have cook times that are in the hours. Here's one that takes over a day to cook. And yeah, so as it turns out, if you want to make eggnog using eggs, that takes some time. There are some types of cookies that need to rest for a while, so they take several hours. But generally speaking, you can see that the cook times for these recipes are relatively lower. So that's a little bit of a data quality check, just taking a look and iterating through the cook times. But what we're trying to show is that we can integrate pandas and Sparkle queries and RDF data just with a few lines of Python. Now, if we want to do something more complex, we've got a little bit more of, you want to take a look at it, there's dig this up. If you go into the dat subdirectory, there's something called nom, pardon my names, but nom, working with food. We've built up a little bit more of a custom vocabulary here And this is using SCAs. That goes back to a question earlier about taxonomies. We've built up a taxonomy to overlay on this recipe data. And so we're going to take a look at trying to understand that there are some types of recipes that use flour and eggs. Some of them create dough and others create batter. And so if you want to drill down in this taxonomy, you could say that a crepe is a type of a pancake. It's created using a batter. Whereas a noodle or a dumpling, these are based on dough, pasta being a similar thing. And there are different types of processes involved. When you're creating a batter, you're typically mixing, whereas when you're creating a dough, you're typically kneading because you want to get the gluten worked. So there's different processes associated. So here we're using RDFS to describe a process with a domain and range. And to put it all together, we come up with this taxonomy that describes a couple different ways to segment recipes. Okay, so if I go back here, let's put it all together. We're going to load up into our recipe database, recipe graph. We're going to load that nom vocabulary. And now we're going to query it and say, okay, gosh, for all the recipes that use eggs, flour, and salt, let's take a look. Now, out of these, let's start to look at some of the metadata and see if we can segment them. So effectively, we're applying some rules. We're going to say, okay, does it have butter in the recipe? In addition to what our query says, which is eggs, flour, and salt, when we look at the results set from that query, does it also have butter? And is there some reference to a noodle in the recipe name? Are they talking about spätzle? Are they talking about pasta? Is this a dumpling? Is this some type of a noodle? So we can basically create a couple of types of annotations programmatically and then tally them up. And so you see this here. It's a little bit hard to look at all the raw results. So let's tally this. We'll create a little quadrant out of it. And you can see here that, yeah, if we've got eggs, flour, and milk, sorry, is that what I was using? Yeah, eggs, flour, and milk. Yeah, eggs, flour, and salt. Sorry. If it also has butter, and it happens to be a noodle, well, false true. You can see this sort of confusion matrix, if you will, here. But basically, we can create some rules out of this. So we can say that if it's a noodle and it has butter, yeah, we've got a rule for that. Or otherwise, there's the false case, or it has butter and it isn't a noodle. And we can look at the ratio, the conditional probabilities of these. So we can come out with a fairly good rule set. And then just by hand, by manual review, we'll seed. Here's some ground truth. Here's a bunch of known noodle recipes. Here's a bunch of known pancake recipes. We can run through and score these. And so what we're going to do is take and annotate for the recipes that we know are noodles or pancakes, respectively. We'll add an annotation from our new taxonomy, and we'll say, this is a noodle recipe, this is a pancake recipe. And now, if you take a look at, let me go back to, we've just saved this file out as temp.ttl. So if you take a look under examples, temp.ttl, now you can start to see where some of these have annotations added. Right, so yeah, I don't know if that one's a good example. If you dig through these, we've built up some. All right, so this is a very programmatic manual way of annotating, adding new nodes to the graph. And gosh, I don't know that I actually even ran that. Yeah, here we go. Ah, there we go. That's much better. So now if I look at noodle. Yeah, so now I've done annotations. So what this couple of for loops here have done is to have a programmatic way of applying a simple set of rules based on conditional probabilities, based on a confusion matrix. We've created annotations to now start to weave a taxonomy into the recipes that we have just by adding some nodes in the graph in particular areas. This is a very manual approach. It's sort of it's not exactly human in the loop. There's much better ways that we can apply both machine learning and active learning human in the loop approaches to annotate better. But it gives this flavor of being able to add to relationships in a graph. Okay, awesome. And so now building on that, let's take a look at 5. So this gets back to an earlier question, both about taxonomy, but also about data quality and understanding if we believe relationships or not. And I'm going to accelerate my pace a little bit more because I know we only have about 40 minutes left. I want to get some more question and answer, but we've had some good Q&A while we're going along. I definitely want to show this. I think it's an extremely useful tool. It's called Shackle. And this is a W3C standard now. It's come out in recent times. I think it's only about 5 or 6 years old, really. There are some other variants, but Shackle is the one that's kind of become the standard. So the notion is that we can create rules to describe shape constraints. And the thing that I want to bring out here is that when we're working with graphs, the way that we apply sense making in terms of graph data is by perceiving patterns, being able to use algorithms and queries to recognize patterns. We leverage the emergent patterns in the data. And so if you were to talk about a relational data warehouse and talk about understanding objects, complex objects in a relational data warehouse, there's a term of a data object that we often use. How do we make sense out of the schema and the different tables and joins and whatnots? In graph data, the notion of a data object is essentially a shape, a geometry, a geometric pattern. And that's what I was trying to show earlier with the village example. There is a programmatic way that we can specify geometries, shape constraints, and then apply these for data quality. So with Shackle, what we can do is, here's an example, we'll define a shape graph. We've got some Shackle rules. We can say that for a person object, that we expect to have a person, a given name, a birth date, a gender description, and an address. And then for a valid address, we expect to have a street address and a postal code. So just relatively easy to read. We've got some rules here for the domain of talking about people and where they live, some basic demographic data. If I run this, I will create a small Shackle description. And now this is create a really small graph in RDF. Well, this is actually JSON LD, but RDF describing a person and birth date and address. Real minimal graph there. But now I can run the shape constraints against the graph. And this is using PyShackle. It's sort of an add-on for RDFlib. And what I'll do is I'll take the reports and print them out as RDF. So I apply Shackle constraints rules to a graph, and the parts that are invalidated are sent back as an RDF graph. So I have a kind of transformation that's going on there. It's a little bit hard to read just the printout. What I can do here, I can print out the text. A little bit easier to read here, but you do see where, well, actually we have some constraints, some violations. For instance, the birth date wasn't formatted correctly according to the metadata. And also we can say that the address wasn't correct. There's a violation there. It lacked a postal code, if I recall. So this one record, if you will, this one data object in RDF actually has 2 violations for data quality. Its postal code is invalid and the birth date is invalid according to the rules that we've defined here. Now we can make this more complex, but I do want to point out that, you know, we can take the report coming out of Shackle, and since it's RDF, we can create an RDF graph out of it. Now, over in KG Lab, we've tried to make this a little bit easier to work with. Here, we'll bring in our food graph that we loaded, actually a larger one. And then we'll create a Shackle constraints. We'll say every recipe should have a minimum of 3 ingredients, and we're going to expect that the length of its definition is 50 characters at most. So these are kind of arbitrary, but I'm just trying to apply some data quality rules to say, this is what we expect to see in our data. Let's go find out the parts of the data that violate it. Where are the relationships and the nodes that violate these rules? And so here, just real simply, I will say kg.validate with the shape graph, the rules I've defined here, and the output should be formatted as RDF, as turtle. Boom. So I've applied those rules, and now I can print it out, just a text report again. And you can see, yeah, you know, there are some, so German dumplings, Spätzle, or Kniffels for super saute. I lived for a while in a home where Spätzle was made quite frequently. I have fond memories of that. Some of these recipes have names that are just too long according to our rules. So those are kicked out. Now, if I want, I can also take and run a query against what comes out. I can take and query the results and then produce the results as a pandas data frame. So boom, I can take and start to account or audit my graph data by applying some Shackle rules and come out with a pandas data frame. And so now I've got that in a table, and if I want to, I can visualize that in different ways. You can also take a look at it here in PyViz, and we can show what's going on with these constraints and the ones that are kicked out. But Shackle is really super useful. And you know, up at the top here, I made a point here to a friend of mine, Veronica Heimsbach. I definitely recommend, there's a masterclass that Veronica's been doing. Veronica is a data scientist working at Capgemini. She's based out of Oslo, and she has some really great tutorials about how Capgemini is doing. For instance, there's an audit that they perform for the Norwegian government for master mariners, you know, people who pilot really large ships. They have to go for certification periodically, and it's a very complex process of accreditation. And so to be able to audit that the accreditation process has been applied correctly, there's a lot of rules. Veronica built up Shackle rules and using RDF to be able to run those audits and really streamlined it. And the nice thing is when you look at Veronica's tutorials, they talk about how the rules in Shackle are something that people who run Master Mariner accreditation, they can understand. They don't have to be experts in computer science. They can read these rules and say, yes, you know, Sven has less than 15 years working on a liquid gas tanker, therefore he doesn't qualify for this next stage. So can we take domain expertise and represent it in ways that we can run as rules, we can run with inference and apply to knowledge graphs in a very convenient way? And moreover, can we get some sort of transformational properties where the data quality items that need to be inspected, they get kicked out as their own subgraph. So we get those and we can operate on them and run some visualization. Shackle, really great tool to use. And I should ask if there are any questions about that. I'm doing that. Let me, no questions per se, just yet. I'll take questions as they come. Okay, let's go on to a different area, completely different. Let's talk about graph algorithms. So there's a package called NetworkX that's very popular, also very inefficient. Wait, there's a question. Okay, Ryan, there's a lot of demand for knowledge graph to help members of research center. Yeah, understand what project and expertise everyone else is involved with. Could KG Lab help facilitate? Oh, yeah, absolutely. I mean, this is really where it's built. No, it's a great question. So yeah, Ryan, great question. Can we leverage graphs like this to start to represent discovery of where are the projects and expertise? Yeah, absolutely. And in fact, one of the things that I'll mention there, when you look in the graph community, there's currently a large sort of subthread, if you will, on the subject of personal knowledge graph, PKG. And by personal, what I mean is it's not enterprise scale. It's something that's an individual is using or maybe a small work group is using. And then, of course, the next stage of that is how can different work groups interoperate and combine their personal knowledge graphs, if you will. There's a lot of great work in this field. I'll definitely point toward one of the real leaders. Well, there's a lot of work at RPI. I won't go into individuals, but there's a lot of great researchers there who've been very seminal in defining the W3C standards. And definitely a lot of work for personal knowledge graphs, particularly in terms of healthcare and people getting access to their own medical data, and how can that be applied when you go from one doctor to another. But it also works in research, because I find that a lot of this kind of personal knowledge graph space is where there will be a postdoc who's trying to collect a lot of research together and put it into some form that other people can use. That may be a typical kind of thing that you get assigned as a postdoc to work on. But I've just seen it over and over. And so you have an individual who will be very knowledgeable in a particular slice of a field, and they'll have the crosswalks. They'll understand where are the benchmark data sets. They will have the magic decoder ring for that area of research. And, they've written it up. It's in a half dozen different Google Docs or something. Instead, it would make sense for that kind of research resource to be available as RDF, as a knowledge graph, because then anybody else who's got RDF graph libraries can pick it up and add it to their graph and see where's the overlap, where could we be partnering. It could be that different research teams actually publish RDF graphs of who their principal investigators are, which projects are they working on, what are the metadata vocabularies that they work with, things like that. So to that end, in the personal knowledge graph space, there's been a lot of work in terms of leveraging tools such as, if you're familiar with Rome Research or Notion or Kenobi, there are a lot of tools that are coming out that are really good for taking structured notes. And at the end of the day, you end up with a graph of Markdown. And certainly if you're using Rome, when you take the Rome export, it is a JSON graph of Markdown. And I see researchers using Rome to collect their research notes. So one of the things that we've done with KG Lab is we can take a Rome export and import it, and boom, you've got an RDF graph. So if, for instance, you had different research teams that were taking notes of, what are the projects and the expertise they're working with, and they had these as their own Rome instances, you could export those, import them as RDF, put them together into one KG, one knowledge graph, and then be able to run inference and machine learning on it. If, for instance, you had a lot of research groups together. I think that there's a lot of room forward for this kind of work in the world. And the graph community is definitely looking at where this can be applied. It's got a lot of layers to it, but we've done some writing. I'm in a work group for personal knowledge graph. Yeah, Rome Research, exactly, that's the one. But there's others. There's Kenobi, which is actually semantic. I'll post some links if we can set up some discussions, perhaps on the Slack for ESIP, or I can put it in the document for the workshop here. There's Rome, there's Kenobi, there's a bunch of these that are coming up. But I just think that this idea of people being able to collaborate with note-taking tools to describe their research, and then being able to join that, if you will, combine that across teams by using RDF, I just think there's a lot of room forward on that. I'd love to work with people on that specifically. That was one of the reasons why we started this thing with KG Lab. But certainly if you have areas where you would like to work on that, if you want to collaborate to help get started, or if we can help build out features to support you, please let me know. All right, let's jump into graph algorithms. I want to pick up the pace a little bit. There's a couple of sections I really want to cover. Yeah, well, Project Underlay. Thank you, Ryan. Yeah, there's something called Project Underlay, and yeah, one of the principals there is a friend of mine, and Samuel Klein is one of the researchers there. Really great guy. And yeah, Underlay definitely would be a way of publishing. There's also Solid. There's a number of different projects in the space, and I love Sam to pieces. So yeah, a lot of good tooling coming up in this area. I really think there's a lot of room going forward, especially in the research space, particularly for scholarly infrastructure. That's where I got started in knowledge graph, to be able to leverage these kind of technologies. And of course, it spills over in industry too, because for instance, if you happen to run chemistry plants and you happen to employ 10,000 material scientists and chemists, by the way, you probably have a very large subscription to Elsevier for all the research papers coming out, and you really want to have a knowledge graph to organize that. That's one of the use cases of BASF we're working on. Okay, let me talk about graph algorithms here. Without going into the theory too much, we can represent a graph as a matrix, as a dictionary of dictionaries, a lot of different ways. But what we're going to do here is we're going to load up KGLab with our recipes. And boom. And now let's define a Sparkle query that will just be looking at subject and object for recipes versus ingredients. So we're going to look at these relationships between recipes and ingredients, just kind of a subset of our data. And getting into some of the math, we can also say that could represent a bipartite graph. There are no recipes that are ingredients and there are ingredients that are recipes. So it's a bipart graph. There are two different disjoint sets that are connected with each other. And we can represent this as a digraph in network X. So what I'll do is, again, we've created a knowledge graph with the recipes. We've defined a query for this relationship for a bipartite graph between recipes and ingredients. And then here we say, create a subgraph, and then build a network X graph, a directed graph that's bipartite out of that. We end up with an X graph. So let's operate on that. First, we'll take a measure using a graph algorithm to calculate density. And if you want to drill down, there's more definitions of what does density in a graph mean, but it's a useful measure for understanding the sparsity of it, for being able to estimate some of the computational complexity costs. Different things rely on this. In our case, we end up with a density measure of 0.16 and change. Yeah, it's not particularly dense. It's relatively sparse. We can also take and run some algorithms. Let's take a look at the node butter. And this is make sure that we've got an ID, an identifier transformed in the same transformation space. Now let's use that as a starting point into the graph. And we'll conduct a breadth first search across all the graph, starting with butter as our entry point. We'll look at depth limit 2. Let's see how many edges. 0. So there are no neighbors identified by breadth first search. And the reason is that if you go back to our graph visualization, butter is a terminal node, and we have a directed graph. So there's nothing really that butter connects out to. So what we're going to do instead is convert our graph to be undirected. So it's an undirected graph, and now we can apply more algorithms to it more fluently. If we go back in here and look at this, now we can say, wow, a lot of things connect into butter. A lot of different ingredients are close to that. So we're starting to look at some of the neighborhood for it. We can start to address similarity. But first off, let's take a look. If we do consider this to be a bipartite graph, one of the things that network X will do is you can actually decompose it in the different bipartite sets. So you can peel off different segmentations, if you will. You can also do, here's something, a little bit of a topology analysis. This is something called a triadic census. So we can count the different triads that are within this graph. And if you've ever worked with topologies and graphs, there's a paper that describes this in much more detail if you looked at Bedham-Gell. But basically, there are these different identifiers for different known types of triads, different shapes. And frankly, this analysis is really useful. If you look at the use case at Novartis, the research agenda at Novartis for pharma research is actually driven by triad analysis with graphs. What they do is they construct a really large graph of references to different molecules, different compounds in research about pharmacology. And so they look at the papers, they look at the references to diseases, references to genes, and references to compounds, and they do a triadic census and then sum those up and create a probabilistic triangle, if you will, of we know that these particular compounds are associated with these particular genes and these particular diseases. Now, that doesn't tell you exactly the direction. It could be that a compound is known to be causing a disease, or it could be that it's suspected as being able to cure a disease. But anyway, there's a relationship. And by doing a very simple triadic census on huge amounts of graph data, Novartis is able to go back in and run this past their biologists and say, hey, we found some relationships here. And in most cases, what they find, Stephen Reiling has really great talk about this, but what they find is the biologists will come back and say, yeah, we know about most of this. But there's one case here, we've never seen it before. Gosh, let's go back into the wet lab. Let's try that out. And what they found is that by experimentation, they can validate a lot of what's predicted out of the graph analysis. And so what this means is that rather than having to do their experiments one by one, test tube by test tube in the wet labs, now they can go back and prioritize a research agenda to sort of parallelize the research based on probabilistically where are the most interesting parts of uncertainty that have been identified by this graph analysis in terms of what they didn't know about coming out of the scientific literature. So triadic census, really handy, very useful in research. Sorry, a little bit of digression, but I thought that might be useful to kind of ground it in a use case. Let's try, we've got our graph here. Let's try running an algorithm called degree centrality. This is very similar to calculating PageRank, which is eigenvalue centrality. But anyway, what we'll do is we'll take a look and what are the most connected, most important ingredients? Flour, egg, salt, butter, milk, sugar, what you would expect. Garlic and bacon, sadly, are not at the top of the list. They're definitely not looking at my kitchen. But you know, this starts to give you some ranking of what are the important contributors. And so this might be really interesting if you had a graph of different research labs and where their areas of expertise were, you could start to rank things and start to understand where should we look at next. We can also plot it with matplotlib, a different way of doing visualizations. So we'll assign red to the ingredients and then blue to the recipes. And we can start to peel out based on centrality. We can start to see some tension there. We can do a little bit more deeper analysis of this using K-cores to like peel off the layers, if you will. And now let's visualize that. Yeah, and you can start to see that some of the ingredients, this is a different view of centrality, really, if you will, but there are certainly some ingredients that are much more popular, much more connected to the others. Garlic just really isn't represented here. Flour, water, those kind of things definitely are. If I want, I can peel off, basically, let's take a look at sorted order based off of K-core analysis. And we can see that, we'll peel off. Flour is very connected. Egg comes next, salt comes next, butter comes next. So basically you can pull out what are the major components and then start to look at the lesser components. And here we'll show you doing the same thing with PageRank. And just real brief, why is this important? Well, graph algorithms allow you to get into the data in ways that graph queries cannot. And certainly when you're starting to assess uncertainty and go after the unknown unknowns and work with complex patterns, graph algorithms are a way of being able to do those traversals in ways that queries don't necessarily handle. And in terms of where does this get used in research, I highly recommend looking up, there's a project called Foodome. And this is Albert Barabasi. If you don't know, there's a researcher named Albert Laszlo Barabasi, who's really famous. He's invented a field called network medicine. And there's a spinoff that they have, this is from MIT and some others, but they're doing food science. And so basically they look at ingredients in food, they look at gut biome analysis, they look at DNA, genomic analysis of gut biome of individuals versus diseases that are being expressed. One of the things that Barabasi has shown is that FDA currently only lists 150 nutrients that are allegedly important for dietary analysis. But if you look, there are approximately 26,000 ingredients that are common in food. If you look at the ones that don't make the threshold cutoff of 150, if you look at the lesser ingredients, but you look at the connections between certain ones, it turns out that in terms of carcinogenic influence, You can see this certainly in the analysis of the Mediterranean diet. But if you look at the lesser nutrients and you look at how they have interactions with each other, it turns out that the ones that don't make the 150 cutoff are actually turned out to be much more important when you look at genomic analysis of carcinogens. And so the FDA had arbitrarily said the top 150 are most important. As it turns out, Foodoma is saying, nah, if you look at a much larger scope, you end up with better science. The problem is you end up with a graph that has like 10 to the 23 ingredient elements in it if it were not sparse. So it's very complex, but this is also our path forward for a lot of cancer genomics. Oh, great. Thank you, Ryan. Yeah, Barabasi has, yeah, the Nature article from Barabasi et al. Really fantastic. Yeah, this is actually the same thing I'm talking about here. It's the same thing that Nature paper was talking about. Really interesting work. We just gave him the award this year at Knowledge Graph Conference. So I just want to express that doing this kind of algorithmic analysis really comes out to being important for science. You know, I'm not going to go into detail. There's another package called iGraph, and there are things that you can do there. There's another package called cuGraph, which is part of Rapids. We have integrations with that. I'm not going to really deal with it because it gets into much more time. Real quick here, I want to cover two other topics that I think are very important. One of them is about inference. And so I'm going to buzz through this one quick so I can get to the last example. But what we've got is it's a real simple example involving a tribe of Vikings. And we have the family relationships that are described. If you want to take a look, the data is over here. It's called Gorm TTL. So we've got a tribe of Vikings and some of the things they like to do: fighting, berserking, raiding, stuff like that. And so what we're going to do is define a small graph for our Viking tribe. And you can take a look at it here. And there's some different people: Astrid, Bodil, Life, a bunch of folks really interested in certain things. We can measure this graph. I'm just throwing this out because it's a relatively unknown graph for us. So I'm going to import pandas, and I'm going to do KGLab, create a measure object. I'm going to measure the graph, and now I can print out how many edges, how many nodes. Okay, so it's 25 edges, 15 nodes. That's pretty interesting. I'm going to do a real quick query, and I'm going to say who is an ancestor of whom. And that ancestor relationship, actually, it's available in the vocabulary, but it's not available if there are no links that are defined here. Right? We have child of, it's the inverse of ancestor, but ancestor itself had not been populated. But we do have child of. So what I'm going to show here is, well, also let's take a look. There's another kind of relation of spouse. Who's the spouse of whom? We have a few of those. So Bodil is spouse of Life. Great. And another question: Vikings, what do they do in their spare time? Let's take a look. Nothing. It's not really populated yet. And this is kind of strange because, you know, from this analysis, this tribe of Vikings, nobody wants to fight. What's wrong with this picture? That's just not very Viking-like. What happens is we've done a very simple expression about this tribe. We have some relationships, some interests. We know that, for instance, Bjorn likes to pillage and Gorm likes to berserker. And we know that pillaging is a form of fighting. And also berserking is a form of fighting. It's just those links weren't explicitly made in our graph data. And so when we go to query it, since it's not explicit, it doesn't show up in the query results. So this is where we can use inference based on OWL, for instance, OWL-RL. So we can do a closure, an inference closure in OWL. What I'll do is use KGLab. I'll instantiate inference OWL closure, and here's my graph. So what I've done is to apply transitive inference across this graph. And now when you take a look at it, what happens is that we know that ancestor of is the opposite of, is the inverse of a child of relationship. So wherever we see a child of relationship, we can go out and populate the inverse of it as an ancestor. So we can build out more relationships within the graph. And when we apply closure, that inference, now we come back and we measure, wow, okay, we've bounced up. We have, approximately 6 times as many edges and 5 times as many nodes. And now if we go back and query, boom, it turns out ancestor of, well, we have a better populated tree. We had the child of relationships before, we didn't have ancestors. So now we can see child, we can see ancestor. When we look at spouse of, now we've got this kind of bijective relationship. So, it's transitivity has been populating it more. And also we can tally, we can say, boom, what are the counts for all the different types of subjects, predicates, and objects. And also we can run a different type of inference. This is based more on taxonomy. It's based on SCA's inference. We can expand narrower versus broader in terms of scope of a taxonomy. And so, for instance, we know that fighting is a kind of hobby. We know that berserker is a kind of hobby. If I run this here, we can use inference to expand the taxonomic relationships as well, not just inverse relationships, but narrower and broader types of relationships. And this is the kind of thing that you see in scholarly research, is sort of these taxonomies of different categories, classifications of research. Some are narrower and broader. And so now when we rerun the query, we see, Gorm likes to pillage, and Bjorn likes to pillage, Gorm likes to berserker. And so now we have some Vikings who want to fight. That's what I would have expected. So real simple example, but it shows how to do some measurements, how to do some inference, transitive closure, etc. And this is also a really good area to explain why we don't use relational databases. If you try to perform transitive closure on a billion element graph in a relational database, believe me, it won't get very far. Even with 10,000 elements in a graph on a relational database, you try to run the self-joins required for transitive closure, the thing will fall over. And so I run into people from the relational database vendors claiming they can do everything, and yet just run a transitive closure and see how fast it falls to its knees. Okay, so that's just a taste of what can be done with inference. There's a lot more in that world. We just really don't have time to go through. But I do want to show 2 other things. I know we're running up on time. One is called statistical relational learning. And this is, there are many forms of it, but we'll focus on something called probabilistic soft logic. And again, the research team on this is out of UC Santa Cruz, Lise Couture. I'm going to bring in a very simple graph. It has a bunch of acquaintances. Actually, it's Lise and all of her PhD students over the past several years. We'll just bring this in and we'll take a look at it. So you can see, if you dig in here, here's Lise and all of her PhD students, where they have lived and what their interests are. Very simple graph. And now what I'm going to do is create a PSL model out of KG Lab. I'm going to ascribe some rules here, some predicates. So I'm going to say, have 2 people lived in the same area? If so, there's a rule. It's kind of predicate. Do 2 people like the same thing? If so, it's a rule. Do 2 people know each other? Are they friends? So there are 3 rules that we're adding to this. And you could define this. Here's 5 ways to describe whether or not people know each other based on these rules. Basically, we can use these to infer, for the people who don't explicitly know each other, can we assume that they probably know each other because they lived in the same place and they had the same interests? Or they were friend of friend? So PSL is showing a way to be able to define rules and then probabilistically infer relationships and nodes that we think should be there, but also describe what's the certainty that we can probabilistically ascribe to a given graph or a given node. Okay, so I'll add this rule into our graph. I'll clear the model and I'll iterate through. We'll create a subgraph of people who know each other explicitly. And then, here's another one. We'll define people who have lived in the same place. And then people who have interests in the same topics. All right, and we can dig into it. But basically, I'm putting together, here's some observations of people who have interest in the same topics. Okay, and now I will load some ground truth. I happen to know that certain people back up here in my graph quite explicitly know each other. We have that as ground truth. Let's try to infer who we think might know each other based on that ground truth, based on probabilistic soft logic. So what I'm going to do is build up a data frame. There's our ground truth. And now I'm going to run inference. This will take a minute or so. I'll let this run. Good, that's complete. And then I'm going to get the results as a data frame. Just taking a look at the top 5. Now we've got from the different individuals in our graph, remember this is numeric representation, so they're number indexes. We have a truth value from 0 to 1, what we believe as far as do they know each other or not, probabilistically. We can also compare that with what we had before. And so we can build up a slightly larger table based on the ground truth. How do the estimates compare with the ground truth? And then here we can take a difference and create a histogram. As it turns out, the probabilistic estimates of who knew each other, in most cases, dead on. Some cases, there was a little bit of error. Let's take a look and see where are those different cases. So here are people that we said either did or did not probabilistically know each other, and here's where it differed from what we understood to be the ground truth. This is a really good way to go in and start to express some domain rules. This is sort of a complement to what we see with Shackle. It's a probabilistic approach. So by combining things like OWL inference and Shackle and PSL, we can get some very different views on the certainty or uncertainty, the data quality within a graph. Okay, Ryan has a point. For social graphs, FOF is a starting point. Yeah, that's a good point. You know, I used FOF because a friend of a friend is really old, well-established, controlled vocabulary. It's very well known, and it's just very compact for a tutorial example. It's not exactly the best. If you were to describe research communities within ESIP, I would definitely recommend using something else as a basis and building out. There are definitely others. There's a lot of different vocabularies. There's prefix.cc and some other kinds of repositories if you want to go search for different vocabularies. And we definitely have some links here, both in the slide deck and in the notebooks about some of those resources. I can point you toward much more, but I would suggest using a different starting point. FOF is just more of an academic exercise. I know we only have a minute left, strictly speaking, but I want to go through a deep learning example also. Just real quick, we have this notion of embedding, which is to say we can take a graph and we can represent parts of a graph or neighborhoods within a graph as a vector. Again, that's kind of a subgraph projection. Great, Ryan. Yeah, I'd love to talk more. We can probably talk on Slack about that. I can definitely point you toward because I've gone through some of that exercise for other projects. So when you're working with deep learning, when you're working with layers, deep architectures of layers of neural networks, the input needs to be vectorized. So when we take a graph, we can sort of shine a light on a neighborhood of a graph and take what information we have there in terms of nodes and edges, properties, and vectorize that, and train neural networks on that, but then run the entire graph through and see what comes out as the predictions from the neural network. And it's really useful. It's called embedding. It's a very hot research topic in terms of graph neural networks these days, but embedding is the general category. So here I'll show a very simple example using what's called vector embedding, a very, very simple case. So I'm going to say, wow, we have a bunch of food data and we have a lot of duplication within our data. For instance, some ingredients might be called pepper or black pepper. We're going to assume they're the same. Vanilla extract, same thing. Carrots versus carrot, same thing. On and on. We can find a lot of synonyms. And, you know, frankly, when you're doing data science work, a lot of the heavy lifting you have to do is data preparation. So this kind of cleaning up the data is really useful. With a graph, you can use deep learning, you can use vector embedding for a lot of that kind of deduplication. It ends up being some of the really valuable cases in both in research and industry. So here I will analyze the ingredients from 250,000 recipes. Should just take a minute or so. And what we're going to do is look at them recipe by recipe. We'll look at the ingredients and we'll find out who's got what. It turns out that one recipe, or there are some recipes that have at least 43 ingredients, some only have 2. But overall, we have about 15,000 different ingredients of all the different variations of them. I'll just pickle that out as a file I can bring in later. And the thing is, I can represent this as a set of vectors, and I can train up a neural network using these vectors. So basically what I'm doing is I'm looking at where ingredients are used with other ingredients. I have a vector for each recipe, an input vector. What I can do now is to use that to train deep learning. I'll use GenSim to train. And there are other exercises we have that use PyTorch instead, but we'll use GenSim here. And so what we'll do is we'll throw in 250,000 recipes. We'll look at the neighborhood for each recipe. What are the ingredients that are being used in conjunction with each other? And then we'll train a deep learning model to be able to recognize those relationships. GenSim, and it's giving me 11. Okay, no worries about that warning. Good. Okay, and now what I'm going to do is just a little bit of Python here. I'm going to describe a similarity function called getRelated. I can take a look and measure similarity from a few different ways. One is to do some quantile analysis of the results of deep learning. Another is to do a Levenshtein distance calculation on the strings. But I'll have a few different ways to describe similarity based on running these functions. And now let's just we'll look at one kind of recipe ingredient, dried basil. It shows up, it's in the top 50, it's very popular. So if we pull a data frame for that, you can see, here are all the recipes that talk about dried basil, but more importantly, what are the variants? What are the other things that are similar to that? So dried basil turns out is very similar to, dried basil leaves is similar to dried basil. And there's also similarity to other types of herbs that are used in conjunction with it. You get into the middle of the graph, or the middle of the curve, you see things like Parmesan and oregano, barley. And then you get in the long tail and you see things like Italian sausage or whole wheat spaghetti, talking about dishes, more composite usage of it, not synonyms, but composite usage. So let's plot this out. I'm going to show a graph. So basically, if I take my similarity measures by using a deep learning model, I can plot out, okay, here are things that are very, very similar to each other. Here are things that are not particularly similar to each other, but they show up together. What I can do is basically run a deep learning model with vector embedding and then flip it around and use the results of that model as a statistical oracle and construct a distribution here. And we can show that there's some inflection points. There's one at about 0.56 and one at 0.47. We can basically segment this graph, this diagram here into 3 different parts: the very similar parts, the mid-range, and the tail. And we can say that the ones that are up here in the head, they're probably synonyms. And the ones down here, they're probably related, but not synonyms. They're hyponyms or hyponyms. And the long tail, they're basically ingredients in some of the recipe. So we can create a rank relation for that and go back and populate the graph. Boom. What we've done here is to create a machine learning model to disambiguate similar terms. And now we could take some of these and collapse them together, run through a different model. So instead of having 15,000 different ingredients, turns out we might only have 5,000 or maybe quite a bit less. And it's going to take some time, but this is a very important kind of work that you can do with graphs. Okay, that's the last exercise I have here. Let me turn off the share. Sorry. Let me stop share and come back on visually. All right, great. So we're up at time right now. But I'm around if I can help out as far as, actually, you know what? I will take discussions and move those off to Slack because I do have another meeting that I have to get to a little bit later. There was an appointment. Let me look real quick. Yeah, I have a work session coming up. So I will have to jump pretty soon, but I will be available on Slack, and also later on today, be around at the conference. Get back to Zoom. I see other people have to hop off to other things too. Thank you very much for the session. Really great interacting with you all. Really great talking with you. And look forward to more discussions later on, especially some of the takeaways, some of the work groups we can have collaborating on things. Thank you very much.